For the online folks, I will start about how the telephone game works, and it is kind of information distorted kind of game. So when the first person in the line thinks about a concept or a word, and it try to pass it to the next person in the line, and this happens, and usually somewhere into the line, the information distorted, and that makes it really funny. Usually I do a online, like on a spot demonstration of it, but I'm going to show a clip for you that the concept is a bike again. And then we have like a giant queue of people. So we want to see that how it goes. And then let's fast forward to it and go very last part of it. So the three last people get this type of information. And so as human beings, we are not at receiving data and information and communicating it. In daily life, it happens whether you want or not. And this is like a really interesting challenge. So usually it happens without we knowing, with like a significant other, with like colleagues, and if we remove one of the people in the queue and add a robot in it, can we kind of focus on making sure that the information does not distorted, and we can give the information to the next person in the right way. So this is like the all of what I'm going to talk today. So right now, whenever we have a human-robot interaction, the interaction is not very good. For example, in the first video, if you see a teleoperated robot and they're not having like the officer is kicking that robot away, or if the robot having a conversation and you look at the person is not very considering the robot as a person to talk, but look at the camera or like the operator of the robot to show like its surprise. So I believe for a better human-robot interaction, we need to make sure that with the noisy data, with knowing that human can be relaying the information not at ease, we need to design robots and design like algorithms to look at the information, predict human information, and try to understand and predict humans' behavior. And also, we want to design robots that can communicate the information in a way that the human, co-located human, can understand it quickly and easily. So my vision is that if we want to see robots in our daily life, we need to refine HRI into an art of understanding and responsiveness. And as I said, it is necessary for having many interaction in days. So I'm going to divide this talk into two. The first half of it is going to be having a human with in a setting, how we can make robots that can predict and understand human behavior. And since it's a broad scope, we are going to focus only on human-robot conversational group and focusing on social robots. And the projects that I'm going to show you is based on the three places that I work with. The first one is Direction Robot at Microsoft Research. which giving direction to the people. So we have a robot at Microsoft Research. The challenge, like the goal of the robot was giving direction to the people. But over the time, we find out that it is very challenging to even know when the user wants to interact with the robot or not. So my office was like kind of close to the robot, and whenever people passing by that robot, the robot starts saying that like, "Can I help you?" And it was like kind of like driving me crazy at the end of it. So because I was hearing it so much. The second robot that I worked on was the character robot at Disney Research. And the goal of having this robot was to implement it in to the entertainment parks, and it can interact with the human beings. And the third robot that I was working on was robot RoboV in Kyoto, Osaka, actually the place. And we have a real world hat shop that these robots were help the owners to sell hats to customers. So for these robots, the challenge was to approach to the user and also to interpret and know the what type of behavior the customer is taking. So the contribution for this part was to understand how people make a group, make a conversation, how the robot, and the challenge was that how the robot should approach people, how to interpret and predict human behaviors. So first, we needed to create a data set to understand that is our people form a different formation or form a different setting while they're working with a robot. So we create data set, and then we try to compare that if there is a difference between human-human conversational group and human-robot conversational group. And what we've done was to try to understand and mathematically formulate these type of differences. The next challenge was that to understand that who is talking with whom, the same problem that I talked in the first video. And then we needed somehow to characterize these type of interactions. And then the last two of it, which I'm going to focus more, is like if we have a noisy data, if the sensor of the robot does not work well, can we still have a good data or like understand that error is happening? And the last one is to identifying the focus of attention based on the behavior of the people. So just for sake of completeness, I'm going to introduce like three data sets that we collected, and it is available if you need it for any of your research. So the first one is in Disney Research, just a minute, and we have data of human-robot conversational group and human-human conversational group. The second data set is the Babel data set that collected in Atlas, and we were studying people that how they form a conversational group, and we recorded the head orientation and position of them while they were having a conversation. And the third one was the HRI proof of concept at Microsoft Research, which we have like the data from the viewpoint of the robot that I showed you. And we have people kind of like having conversation with each other with a robot and a couple of scenarios. So the takeaway is that we collected human robot data sets for analyzing and testing of our approach. I'm going to skip like the other contribution and go to the last two, which is detecting missing people. And for this one, when we have a human and a robot talking with each other, behind the scene, this like pipelines happens. So a user initiates an interaction, whether by saying something or approaching to the robot. Then we have robot sensors that they are going to be like depth camera, RGB cameras, and many sensors that robots can use. These sensors input goes to human detection algorithm, so we can understand that there is a human and interacting with a robot. Then we have like group detection, and all of these data goes to an interaction engine, and that interaction engine decide the right set of action for the robot. For example, in this case, the robot says respond back to the person. So the problem here is that the sensors are not perfect, and we can access to 100% accurate data. And as a result, the human detection does not work well. The group detection does not work. And so then what happens is that two scenarios happens. One, we are detecting less people. So for example, the person initiates the conversation, and since the robot cannot see it, it doesn't take any action. So it is going to be like frustrating. The user might think that there is like something is wrong, or the robot is ignoring me. The other problem is detecting more people. So for example, a person is just passing by, and the robot thinks that it is a part of the conversation. And then we have, again, like a wrong set of interaction. So it might says that like kind of like revealing sensitive information. So our method is that look like the previous person in the line give you a falsely information, but based on your reasoning, we want to say that although I cannot see a person in this group, based on the evidence I have, there should be a person at this location. So we can have a right set of action, or be a little bit like conservative. Like, for example, I might be like, my sensors might not work. Can you move a little bit? So we kind of like correct that one. So how we can do that? While I was cleaning the data sets, I find out that if we have the conversation of the same size, for example, these like a conversation of size 4, and we pick two random people and try to overlay and like transform those two formations on top of each other like this. If I do it for all the sizes, all the formations, I'm going to have a heat map like this. So if I know the position of a robot, which is like 0, 0, I kind of like know that based on the size of the people where they are going to stand. So I'm going to give you an example here, and we train a classifier for it. So imagine that we have like 4 people in the conversation with a robot, and then a new person joins. In this case, people are going to be welcoming. So they change their arrangement, and they move a little bit more toward the robot to be welcoming. And based on that, the robot says that, okay, probably based in this transformation, we have like 5 people, not 4 people. We trained and tested this model on 2 data sets, Salsa data set and Babel data set. And the result shows that these classifiers are very good and accurately can detect the missing person in the conversational group, and also they can show or predict where is the position of that person. So I'm going to give you a demonstration. So we have like 4 people here, and all of them are wearing motion capture reflective markers. So the robot knows their position. But the person who is going to join the robot does not know anything about it. And still, it can detect that person and look at that person. So the takeaway of this project is that although the errors can happen, we can detect them and try to have a plan for it. And the last project that I'm going to show in this set of like project is identifying the focus of attention. And focus of attention is most of time is like the person who is talking in the group. And for example, right now I'm the like speaker. So if we think it's a kind of like formation, most of you are looking at me. And it is necessary for humanoid robots to look at the person who is talking to make sure that the conversation is kind of smooth and there's no weirdness in it. But the problem is that most of the algorithms that detect focus of attention, either using visual cues, like they look at the lips of the person who is talking, and by the movement, they understand this person is talking, and probably it's going to be the focus of attention. But that does not work properly thanks to COVID-19, and people are wearing masks. So that is like a fail. And then, or many robots are using audio cues, which look at, they have a microphone array and they look at where is exactly the source of the light, and source of the sound. And in the amusement park, especially in Disney parks, that is not the case, because what if we have like someone louder, or it's going to be noisy, or even like microphone arrays inside the robot usually does not work because of so many like sound and noises inside the robot. So this is not accurately working. So my observation was that whenever we have a person or an object of that is the focus of attention, people are going to, like the other people in the party are going to shift toward that object, and they look at that object. And based on that observation, we had the hidden Markov model, which kind of use it. We use hidden Markov model to predict the focus of attention. And the nice thing about hidden Markov models is that there are like hidden states, like where is the focus of attention. People are not saying it like with words or like any kind of, but there are some type of like behavior, like looking at that, which we can mathematically calculate and try to use that one to find out what are those hidden states. So we start with giving equal probability to all the people in the scene to be active speaker. And after that, we look at the gaze direction of each people. And the nice thing about like this approach is, so because this person, and this is like head orientation, not exactly the gaze. When the gaze is like this, there is high probability that this person is going to be the focus of attention. And if like that gaze or head orientation shifts, then we have the less probability of that person is going to talk, and more probability that the second person is talking. So we we gave a Gaussian normal distribution for giving a gaze and the probability of who is going to be the focus of attention. And after that, with a set of observation, so knowing the gaze of all the people in the scene, we tried to calculate the probability of each person being the focus of attention. And after that, we have a forward algorithm that look at the state of the robot right now and try to predict who is the focus of attention in the near future. So we try to like, and after calculating all of them, we go with the person or the object that has the highest probability. I'm going to show you three videos about that, how it is this approach is working. And before doing that, I'm going to tell you that the robot is does not have any microphone or cameras. And the only information that is related to the robot is head orientation of the people in the scene. And so the robot is kind of detecting who is talking right now. But the nice thing about this approach is it is not only about the people. Most of the algorithm that I show you is looking at a lip or sound, and they don't consider the probability of other objects being the focus of attention. For example, if I if someone run into this room, probably all of us like looking at it, and then that is not going to work. So the second one I'm showing, without telling the participants, I bring a poster into the scene, and because it was kind of like surprising, it grabbed their attention, so the robot knows that what happened. And then over the time, the participants lost their attention, and they go back into the conversation, so the robot follows. And the last thing is that, which was surprising to me, so if we have a scenario that we have only two participants looking at each other, so how the robot knows which one is going to talk? And surprisingly, this is still like working. So you get the idea here. And so the takeaway is that with hidden Markov models, we can detect the focus of attention of the group. And so far, I said all the contribution that I've done in the first half of the talk. So the takeaway from this part is that we can provide the data set for community to use, and we can understand the differences between human-robot, human-human conversational group, and then we can detect conversational group. We detect the noisy data, and we can like predict human behavior in that. So I'm going to go to the second part of the talk, which is if the robot has an idea or information, how the sorry, do you have a question? Sorry.
Well, I have a question. Could you elaborate a little bit more why it works for two people? Because like
That's a great question. Yeah. So the reason that it is working is whenever the two people are talking with each other, one person is trying to like speak, and then the other person kind of like nodding or like trying to be responsive to what as you are doing right now. So I'm not like really moving my head, but you are doing like that. You are acknowledge like my thing, and then this when that happened, our algorithm because it's on the 3D, it kind of understand that this is like happening in the scene. So if we have like a person who does not like acknowledge, then we have like a problem. Yeah. So back to the slide. So if we have a robot and having an information, how the robot can convey that information right to the people. And this is like a very challenging because as our attention spans are like getting reduced and reduced, we want to know the information that like we need in a short amount of time, and we want to do it fast. So I don't know if you ever search for a data on the Google, and then there's like a huge text, and then you don't want it. You just want to know the information you want. So this part of the talk is going to through like three steps. One is that what information actually people need from a robot. And the second part is that how we can use new technologies to convey information that people want. And then it is kind of like exploring the opportunities and possible ways of the information, like what is the limit of information that we can convey. So in the first one, we've done the study of people working with a robot, and then they don't know what exactly the robot is doing, but after like working and doing the task, we asked them that what type of information you wanted to know from the robot. So the takeaway here is that we have a list of information that people wants to know from a robot. The second one is that how we can use new technologies to convey those information. For example, when a person is collocated with the with a robot, uh, the person wants to know that what the robot is doing, where it's going, and what is the next direction of the robot. So we started using augmented reality to not saying like where the robot is going, but kind of like showing that information to the user. So there are like three sets of project. One is like showing where the robot is going to go. The second one is to showing the camera feed of the robot on top of the robot. And the third one is that showing the information that if someone is teleoperating a robot, what input to the system is going to actually do with the robot. So sometimes it is challenging to teleoperate a robot because you don't know what does, for example, this button do, and you don't want, and if it's going to be like a very risky situation, you don't want to crash into someone, or you don't want to like break the robot. So with the change of the information representation, we can reduce the workload of the people and make the interaction much more safer. And the last one is that exploring of what is possible type of information we can convey. So, for example, can we convey affection? So we started looking at how people are hugging each other, and based on that, we create a soft robot which is kind of like actuating and applying same amount of force, and we stuffed in into a giant panda bear. And um, we didn't did a full user study with that, but when we were demonstrating it in exhibitions, children like fall in love with these type of robots. The second one is that conveying emotions. Can we like imagine a user goes too close to a robot, and can we convey this information that like don't come close to me, I'm dangerous? So like by kind of like doing what animals do. So the pufferbot project was an expandable structure on top of the robot, and whenever the user goes close to the robot, and the robot expands to convey that information that we are the robot is dangerous. And the next kind of project, which was led by our very own Rio, is how to use again, like a robot, and convey the information from virtual world to the real world. For example, if the user is wearing a virtual virtual reality glasses, and interacting with a chair, can the robot bring the chair so it become more from like the virtual world, like that information conveyed to the real world? And the Roam Shift project was doing that by using an expandable structure on top of the Roomba. So with that, we could change the position of the artifacts and try to make it more real. So this was again like on the body of work that how we can, what type of information we need to convey to people, and how we can do it. So the future work is that if we have a robot in the scenario, and we are playing the same game, can the robot understand like what is the intention of the first person is, and if there is a noise or anything, like correct it and pass it correctly to the next person? So that is going to be like the near term research question that I have, and I want to work with, is how to integrate social awareness into HRI, and or how to use explainable AI into HRI, and enhance it, and also how we can use the LLM models to and then multimodal AI to make the HRI better. And these questions are necessary for my long-term vision, which is refining HRI into an art of understanding and responsiveness. I want to thank all my collaborators for helping me and for these amazing works. And also, I want to thank the artists who helped me with the figures, videos, and everything. Thank you so much for listening, and I need to take any questions.
So, okay, that's a good thought. So when you're talking about like you want to know like what kinds of information you want to know from the robot, wondering like how like the trust in it varies, like like would they want different information if they perceive the robot as like big or dangerous, like a Q1?
Yeah, that's a great question. So, oh, sorry.
Oh yeah. So my question is about like how like trust in robots affects the kind of information people want to know from it. So it's like, do you want to like know any different kinds or more kinds of information from like a robot that's big or one that's like dangerous versus like one that's cute?
Yeah, thank you. So the question, just to make sure I understand it correctly, is that how does embodiment of the robot changes the information that people needed from the robot? And that is like the answer is yes. So when we have like a big robot, people's like information that they needed or they like in the survey they wanted to know is regarding that is it safe to go close to the robot, or where is like the next direction of the robot? So that like most of them are like safety concern. But for aerial robots, the information that people wants to know is like more like kind of like privacy concern. Is that drone recording me? Where is this? So I think depends on the embodiment of the robot, that information changes. And so far we have the data for aerial robot, large ground robot, and small ground robot. But as you say, for the social robot with the cute robot, and those are going to be probably change a bit.
Understood you correctly, you wanted to also detect in the future the emotions or of the humans, and how do you plan to do this? By, for instance, facial expressions, like the basic emotions by Eggman, or by, I don't know, by the voice is high pitched or low pitched or whatever, or how do you plan to do that?
Yeah, so the question, if I understand it correctly, is that what are the next step to understand human emotion and convey it to the robot? So there are many like many kind of features that we can use, like social like facial expression is like a good one. As you mentioned, it is going to be like the pitch of the voice of the person. And for me, I believe that those are very good features to use. But as a continuation of like my work, I'm more interested that, for example, if you feel unsafe around the robot, maybe you don't show it by your face, but you go a little bit, move a little bit further from the robot. So my intention or my next step might be like, again, looking at the position of the people and try to see if we can get any information from that.
Thank you.
So yeah, I think health orientation one is quite interesting. It looks pretty accurate. But on the other hand, like a downside, especially compared to visual aids or the audio cues, is that the participant needs to wear the hat, right? So in that case, for example, are you using that just only for the data collection, or is that like a front end camera, for example, or if I'm looking at the camera, does that camera also accurately detect the head position which works correctly?
Yeah, so I think the again, if I understand the question correctly, is that currently the work using motion capture cameras and how we can like generalize it to the space that it is not augmented with like motion capture or like so to answer that question is is we somehow need like head position and orientation of the people for that algorithm to work. And currently, like for example, in the video that I showed, I'm going to go back. Give me a second. So for this one, in again in the Kyoto University, so the person is not wearing a hat. We are using Kinect to kind of understanding what are each of the joints are. And then we are using like multiple Kinect. We again like augmented the
Connect on around the environment.
Yeah.
In the
Yeah, in the hat shop, yeah. And again, the data is not as clean as like motion capture camera, but still like with couple of like at each position we have like at least 3 Kinects that kind of giving us the orientation, and we think that we are going to use that one. But again, like as you mentioned, in the we were using motion capture and we kind of like augment the person. Now we are like augmenting the whole store with like multiple sensor, and that is like very challenging. So we cannot use a robot in any like environment, unfortunately.
By the way, this is surprising me. Is that like an ongoing work you cannot see?
Oh no, we are yeah
You just gotta see.
you know.
Yeah.
Yeah, so the reason we are under like for the papers we're under review, so I didn't like add it here, but I'm more than happy to talk about it.
Impressive performance
Mm-hmm.
there. Yeah, and I'm not so worried about what the sensing technologies are, because sensing will get better, and it will be ubiquitous, it will be cheaper. I guess I'm wondering what what do you do with the information that the person is putting it on their head?
Yeah, so I'm going to give a little bit more background of it. So there is a hat shop in a shopping mall in Osaka that we are using for implementing our algorithm. And the goal of this project is that how we can teleoperate the robot so they approach people and try to sell hats to them. And when we have like an owner, he is like very smooth talker, and he knows that like the robot cannot go and then say like buy this hat. So it is not a good like strategy. But like the person who is like owning the shop, we interviewed him, and he is looking at the like the clothes that the customer wearing. Is he wearing a hat or not? Is like the person touching multiple hats or not? And all of these information, that's like how many hats she just looked, or how many she tried. Is she use a mirror for like seeing herself in it or not? All these information gathered to interaction engine, I get, and he kind of like decide how should start the conversation. So all of these like information that we are gathering is pieces of like information that the shop owner was like looking at, and we are hoping to use it to have a better customer care robot.
I also have the same question to that conversation one as well. So right now, like, it looks like algorithm works pretty well. That what do you want to do with it? Like currently, it's just kind of heading to the person. That looks good. What's the goal of that?
Yeah, that's a good question. So the question is that what is the application of like focus of attention with a robot? So it can with the gaze we were just showing that we can detect the focus of attention correctly. But focus of attention can use in multiple scenarios. For example, like imagine that I'm going to give an example that a customer is like at the hat shop and she's saying that like, oh, I like that hat better. So the robot might not like understand that what does that means. So with the focus of attention, we can understand, like give more context to like language models that these like referral is pointing to this object and like having a smoother conversation and interaction in the scene.
I'm wondering if you kind of try to test what the precision of the sensor has to be, because I fully agree that the sensors will be better, but the thing is that before we like make it to the market, we should know, for example, like if the robot is wrong, I don't know, 10% of the time, the conversation doesn't really flow anymore because it's too often. Yeah, it's starting to be bothering. And I guess such tests would be challenging to actually do, but do you have any?
Can you elaborate on which sensor are we talking about? Motion capture or like this?
Let's say we detect the point of attention of the person. And thanks to that, we, for example, can say what does that have. But of course, this is not always perfectly detected. So then, let's say we have an interaction like the one that is in the group, and the robot is paying attention to who is speaking. But then, what percentage should be correct? Like closer to 90% or 50% would be already okay, or 99%.
And again, like we are talking about the accuracy of the sensors, not the algorithm, or the algorithm. Yeah, so we tested the algorithm in like I think it was like 20 minutes of interaction, and then we have like those like data and
So you're asking how good is good enough? Yes, how good is good enough? Exactly. If you like, do you have an idea how to validate?
So for validation, it is kind of easy. You have like the interaction session, and then you show those videos that asking like someone to annotate those videos for you that at this point of time with like if I show you this conversation, who is like the focus of attention, and who you would like, if you were in this situation, who you would look at. So we asked them, we annotated the data, and we like have the answer to that. But the question that how accurate is good enough, I believe that it depends on the interaction. Sometimes like when you're talking to someone, they don't look at you and kind of like showing that they're thinking. So if there is no need to like always look at the person and being like accurate. So that's not like really sensitive, but I think that I can imagine some scenarios that it kind of like backfire and like make the not detecting it correctly might like interrupt the interaction. So for me, in the human robot interaction, like 100 is the actual number that we need to reach. But other than that, we need to just be conscious to we plan that somehow that the error happens, but what is the worst case scenario, that how we can like don't lose the interaction, don't lose the interest of the person.
What I was more thinking, like, it's that it's good to think about it when the interaction crashes, like exactly you name it really nicely, yeah? Good enough. But it is not good enough, so we shouldn't really rate, start a product more annoying.
Yeah, I think that's like definitely like moving forward to actually having it into in the real world. That is exactly what we need to do. And I'm going to say that like for that we need more robots in the real world. So most of time we are having robots in the lab, but we need like more robots in the wild.
My question is about the data set you're training, the formation one. So when you're training the data set, the original data set only have humans, right? There's no robot. Yeah.
So there are like the the
So my question is,
Sorry.
is there will be different when I training the data set with robot or without robot? Yeah. And how do you treat that as a ground truth, as a HRI? Like, is HRI data set have to involve a robot or just only human is the ground truth?
So that's a good question. The question is that is there any difference between like a human robot and human interaction data set? And if there is, how we can make sure that testing is like right. So one of the data set that we collected was comparing human conversational group with human robot conversational group. And we find out that there are two characteristics in any type of like data sets. One is the symmetry, how people orient, like if you think it with the angles, that is like how they position themselves. And then we have another term, which is tightness, how close are people toward each other. So when we like with this one, we find out that there are many many features that changes these two features. So for example, if the robot is big, people tend to stay a little bit like further, or if the robot is small, they just like go closer. And we have like a set of like features that there is differences, but with the angular term, people always stay in the symmetric formation. If we have, imagine if there is like again like 3 or 4 people are talking and there is like chair or like it is in the busy space, then that like changes it. So our research shows that that happens, and but we can kind of like mathematically like formulate it and like consider it as a factor so it doesn't like mess up the like whole algorithm.
So you showed us the example with the guiding robot and as well as the robot in the hedgehog. Do you think that those kind of robots have a future? Because both of those scenarios could be just reused with a map or just a salesman who is in the shop and works there. So yeah, do you think that like those kind of scenarios have a future, or do you think that you should rather relocate those resources onto points that have a real impact, for example, in for elderly care or for I guess for childcare maybe also.
Yeah, so the question is that is the project that I work on was realistic enough for and have any impact, I guess, question. And regarding the, I'm going to go back to um, this slide. So the goal of this project is it is a giant project. It's a Japan moonshot project, and the idea, like, there's like many like project that happenings within that longer vision of Japanese government. And their idea is that at some point of time we have like elderly people who cannot run their businesses. So they introduced an idea of like avatar, which is kind of the idea of like elderly people can teleoperate their robot and run their businesses. So we are exactly like for this project, we are exactly like moving toward that direction, that how we can augment elderly people to do their daily task, to run their businesses and be impactful for this society.